A river in the sky can carry more water than many rivers on the ground. These long, narrow corridors of moisture stretch for thousands of kilometers across the atmosphere, transporting enormous amounts of water vapor over the oceans before sometimes unleashing extreme rain and floods when they reach land. But scientists have now discovered that atmospheric rivers are doing something much less obvious before they ever reach a coastline. They are changing the temperature of the ocean beneath them. A new analysis of more than 4 decades of satellite and climate data shows that atmospheric rivers can influence the development of marine heat waves across the North Pacific and North Atlantic. Even more surprisingly, the effect can reverse with the seasons. In winter, atmospheric rivers often help warm the ocean's surface. In summer, they can cool large regions instead. The discovery reveals a previously overlooked connection between two major forms of extreme weather: rivers of moisture in the atmosphere and heat waves in the ocean. Marine heat waves are not simply warm summer days at sea. Scientists define them relative to what is normal for a specific location and season. In the new study, an event qualified when sea surface temperature remained above the local 90th percentile for at least 5 consecutive days. That means a marine heat wave can occur even in winter. And for marine ecosystems, the difference between normal and unusually warm water can matter more than the absolute temperature itself. Fish, corals, kelp forests, plankton, and other organisms are adapted to particular temperature ranges. When the water remains unusually warm for days, weeks, or months, animals may migrate, reproduction can fail, disease can spread, and entire food webs can change. Some marine heat waves have already caused mass mortality, damaged fisheries, and transformed ecosystems across enormous areas. Scientists know that long-term global warming is raising the baseline temperature of the ocean. More than 90% of the excess heat trapped by greenhouse gases has entered the oceans. But that does not explain why a marine heat wave suddenly begins in one particular region at one particular time. Researchers therefore searched for shorter-term atmospheric processes that might help push the ocean across the threshold. One candidate was hiding directly above the water. Atmospheric rivers are usually discussed because of what happens when they reach land. A powerful one striking California, for example, can transport tropical moisture toward mountains, where the air rises, cools, and releases enormous amounts of precipitation. But most of an atmospheric river's lifetime occurs over the ocean. There, it carries not only moisture but clouds, strong winds, warm air, and unusual humidity. All of those factors influence how heat moves between the atmosphere and the sea. The researchers analyzed marine heat waves and atmospheric rivers across the North Pacific and North Atlantic between 1982 and 2023. They expected to find some connection. What emerged was much stranger. In winter, marine heat waves across much of the northern oceans tended to occur during periods with unusually frequent atmospheric rivers. But summer produced almost the opposite pattern. Across large areas, marine heat wave peaks were associated with fewer atmospheric rivers. The relationship formed a broad horseshoe-shaped pattern over the North Pacific, with regions of increased and decreased atmospheric river activity surrounding one another. The team then looked backward in time around each heat wave. The signal appeared before the ocean temperature reached its maximum. Atmospheric river anomalies often emerged more than a week before the marine heat wave peak and became strongest roughly 2 days before it. That timing was important. If atmospheric rivers appeared only after the ocean became unusually warm, the ocean might simply have been changing the atmosphere above it. Instead, the atmospheric pattern appeared first. Something in those rivers of moisture was helping control the temperature below. To understand what, imagine the surface of the ocean as a giant heat account. Sunlight deposits energy. Infrared radiation can remove or add energy depending on atmospheric conditions. Evaporation removes heat because liquid water needs energy to become vapor. Direct heat exchange between warm water and cooler air can also cool the surface. An atmospheric river changes several of these processes at the same time. And some of those changes fight against one another. First, atmospheric rivers bring clouds. Clouds block part of the incoming sunlight, reducing the amount of solar energy reaching the ocean. This tends to cool the sea surface. If this were the only effect, atmospheric rivers would simply suppress marine heat waves. But they also bring extremely humid air. Normally, relatively dry air moving over the ocean allows substantial evaporation. Water molecules escape from the surface and carry heat away with them. Under an atmospheric river, the air is already filled with moisture. The difference in humidity between the ocean surface and atmosphere becomes smaller. Evaporation weakens. The ocean loses less heat. It is similar to trying to dry wet clothes in already humid air. When the atmosphere is nearly saturated, evaporation slows dramatically. Atmospheric rivers can also bring unusually warm air. This reduces the temperature difference between the sea and the atmosphere, weakening the direct transfer of sensible heat from ocean to air. Together, these processes act like a temporary lid over the ocean. Clouds reduce incoming sunlight and try to cool the surface. But warm, humid air reduces the amount of heat escaping from the ocean and tries to warm it. The outcome depends on which effect wins. And that changes with the season. During summer, sunlight is intense. Blocking solar radiation with thick atmospheric river clouds can remove a large amount of energy that would otherwise enter the surface ocean. The cooling effect can therefore become dominant. During winter, sunlight is much weaker, so there is less solar energy available for clouds to block in the first place. At the same time, the winter ocean often loses enormous quantities of heat into cold, dry air. Replace that air with a warm, humid atmospheric river, and the heat loss can suddenly collapse. The ocean keeps energy it would normally have released. The same atmospheric phenomenon can therefore cool the sea in one season and warm it in another. Researchers tested this using an ocean mixed-layer heat budget, effectively calculating where the energy entering and leaving the upper ocean came from. Surface heat exchange with the atmosphere was the dominant factor. Ocean currents contributed, but their overall influence was smaller. Vertical mixing and other unresolved ocean processes generally acted to damp the atmospheric effect rather than create it. The researchers also tested whether the pattern appeared in climate models. 15 CMIP6 models reproduced the broad seasonal relationship, and most agreed on the direction of the atmospheric river effect across large regions. That strengthened the evidence that the connection was not simply a coincidence in the observational record. But there is another complication. Marine heat waves can influence atmospheric rivers too. Warm ocean water increases evaporation and adds heat and moisture to the atmosphere. That can modify storms and moisture transport above the ocean. Another study published in July 2026 examined the opposite direction of the relationship, showing that marine heat waves in the Northeast Pacific can intensify atmospheric rivers making landfall on the west coast of North America. That creates the possibility of a two-way interaction. An atmospheric river may change ocean temperature. The altered ocean may then modify later atmospheric rivers. Instead of two independent extreme events, they may sometimes become parts of the same coupled ocean-atmosphere system. Consider what could happen in winter. An atmospheric river passes over the North Pacific carrying warm, humid air. Evaporation decreases, so the ocean retains more heat. If conditions are already close to the marine heat wave threshold, several such events could help the temperature anomaly grow. The warm ocean then releases additional moisture into later weather systems. Those systems move toward North America, where atmospheric rivers can produce intense rain, flooding, snow, and landslides. The heat wave in the ocean and the flood-producing river in the sky may therefore be connected across thousands of kilometers. This matters even more as the climate warms. Atmospheric rivers are expected to carry more moisture in a warmer atmosphere because warmer air can hold more water vapor. Marine heat waves are also becoming more frequent and intense as the background ocean warms. The interaction between them could therefore become increasingly important. However, the new study does not mean every atmospheric river causes a marine heat wave. Their effects vary by location, season, existing ocean temperature, wind, cloud structure, and background climate patterns such as El Niño, the Pacific Decadal Oscillation, and the North Atlantic Oscillation. Sometimes the cooling effect wins. Sometimes the warming effect wins. Sometimes the atmospheric river may have relatively little effect at all. What the study identifies is a systematic influence that had largely been missing from our understanding of marine heatwave development. That could eventually improve forecasts. Scientists already monitor atmospheric rivers using satellites, weather models, and measurements of vertically integrated water vapor transport. Because changes in atmospheric river activity often appeared several days before marine heatwave peaks in the study, including this information in ocean forecasts might provide an additional warning signal. Even a few extra days could matter for fisheries, aquaculture operations, marine protected areas, and scientists monitoring vulnerable ecosystems. And the issue is becoming increasingly relevant. NOAA reported that roughly 1/3 of the global ocean was experiencing marine heatwave conditions in June 2026, with events present in regions including the Eastern Pacific, Northeast Atlantic, Mediterranean, Tasman Sea, and parts of the Southern Ocean. The ocean is not warming as one uniform body of water. It warms through global trends layered with currents, winds, clouds, storms, climate cycles, and now, scientists know, rivers flowing through the sky. The strange part is that these atmospheric rivers carry no visible banks and rarely appear as dramatic objects from the ground. Yet while crossing the ocean, they can alter how much sunlight reaches the surface, how much water evaporates, and how much heat escapes into the atmosphere. A river thousands of meters above the sea can therefore help create or suppress a heat wave in the water beneath it. And as extreme events increasingly overlap in a warmer world, understanding connections like this may become just as important as understanding the events themselves.